Next up, I'm going to introduce our first international liaison speaker, who is Dr. Olivier Robin from University of Sherbrooke, and he works in the Gauss, they call it. So it's Group Acoustique to University of Sherbrooke, and they do a lot of different things. I expect you'll probably have a little bit of an introduction on what the overall group does, but his main topic is going to be on using deflectometry to measure the vibration of overall structures, and he has since, some of you may have seen previous briefs, added the ability to use infrared processing, which improves his ability quite a bit. So what we're going to do here is first ask if Olivier is there and can speak. So Olivier, can you use your microphone just to say hi real quick? Oh, he's not on. Okay. And he was on earlier. Maybe he's taking a break. Okay, so we'll hope he joins us. If not, we'll just enjoy his brief. And actually, Mike has worked with him quite a bit, so he might be able to answer some deflectometry questions if anybody has them, and Olivier doesn't join us. But we'll go ahead and play the pre-recorded talk now. So go ahead, Kelly.
Welcome to this fall CAV workshop. I'm Olivier Robin. I'm assistant professor at Gauss, University of Sherbrooke. I'll first give a quick overview of what is the Gauss laboratory, and then I'll speak of infrared deflectometry, longer wavelengths for wider applications. So where is the Gauss lab? You see this orange rectangle right there in Canada, and more precisely, it's 150 kilometers east from Montreal. The Gauss laboratory was founded in 1984 by Jean Nicolas. There are currently 7 professors at Gauss, and overall we have, depending on the year, we have 40 to 50 people, which involve students, postdocs, research professional, and a technician. We are recognized as the largest Canadian acoustics and vibration research center. Gauss have been awarded several research chairs. There has been industrial acoustics, aviation acoustics, transportation vibroacoustics, and the Gauss has been Center of Excellence at University of Sherbrooke since 20 years. The global research areas of the Gauss include materials, vibroacoustics, tests, characterization, and also active control and structural health monitoring. The Gauss has the chance to have large infrastructures and equipment. Few of them are indicated there. There is a 96-channel WFS for wave field synthesis. We got a 50-channel ambisonic systems, a 3D laser vibrometer, wind tunnel in anechoic room, and high-speed cameras coupled reverberant anechoic rooms, and up to 250 microphones. Concerning collaborations, as an evidence, we are a liaison with the CAV for more than for several years now. But the Gauss is also involved into an international research project, which is the Centre Acoustique Jacques Cartier. So it's finally a France-Canada network between Le Mans, Lyon, and Sherbrooke. And we have collaborations in Canada as well, especially with the CURMIT, which is the Center for Interdisciplinary Research in Music, Media, and Technology, and is based at Montreal. Research areas with the CURMIT are typically sound field reproduction, 3D audio, so you get here an anechoic room validation of a hybrid method, combining a sphere of 50 sources with a circular array of 32 sources. But also at Gauss, we have some interdisciplinary research in the broad area of music and sound. So this is some research that I'm currently handling as a new professor. So you get the special, this include in fact the special audio recordings of skilled musicians and the 3D printing of, of sound patterns that can be the sound directivity of instrument, mostly for dissemination purpose. Concerning dissemination, we do actually a lot of dissemination. We use a variety of media. So there are videos, including spatialized audio. We got videos to explain some classic principle of acoustics, sound spatialization. I do use, from my side, a lot of comics to explain what do we do in acoustics, what is noise, what is deflectometry, and also lead several initiatives regarding the dissemination of research with museums. So we developed Sound Just Sound with Sherbrooke's Science and Nature Museum, which has been awarded the Best Exhibit Small Institution from the Canadian Association of Science Centers in 2020. So there are some pictures of the exhibition just below. And we've set up another exhibition with a museum at Valcourt in Quebec. So this is concerning the how transportation means and why they're comfortable, and what can we do in terms of thermal insulation, acoustics installations, and such kind of topics. Just to let you know that ghost is now becoming crash. These are not bad news, but CRASH stands for Centre de Recherche Acoustique Signal Humain, which would be in English Acoustics Signal Human Research Center. And we're moving to a more consequent structure that include 20 professors from a multidisciplinary angle. So the professors include engineering, so that can be mechanical, that can be electrical engineering, but also medicine and music as well. So to go back to the core of the presentation, maybe I'll do a short introduction to deflectometry, and the idea is to explain you how we are moving to infrared deflectometry and why larger wavelengths will broaden the possible applications of deflectometry. So maybe if we go back to classical vibration measurement on structures, they have been up to date, limited to the location of contact sensors that are usually few in terms of number, and to limit the added mass. And the typical case would be model analysis, as depicted below. But the problem is that for many applications, dense and spatial vibration measurements are required, and that should be ideally contactless, because the mass effect still has to we have to deal with this effect. And for vibration mapping, load identification, structural health monitoring, structural design, dense and spatial vibration measurements are typically required. So the mostly used tool is certainly the laser Doppler vibrometer. So there has been the 2D vibrometer, the 3D vibrometer, now the 3D vibrometer coupled with the robot. Many possibilities, but still, the laser Doppler vibrometer require that we scan the structures. There's a need to go point by point, and the advance in computers and digital imaging technology have led also to the development of several techniques to measure full field vibration. And so this is typically what is done in DIC for digital image correction, and there is also deflectometry as well. So below is a GIF of raw vibration measurements on a plexiglass panel. So it's pretty obvious that we really see, so it's an impact at the center of the panel, and we clearly see this spherical wave that is spreading from the center of the panel and it shows that even on a raw measurement, deflectometry allows to properly delineate the wave propagation as a function of time and space, which is a real important result and has several implications for further analysis or post-processing of data. So, what is the principle of deflectometry? So, it's quite simple. Indeed, there's a reflective surface on which we would like to make some measurements to identify the vibration field. So what we do is that we put a grid in front of this reflective surface, and we are speaking of an optically reflective surface there. And using a camera, we can capture the image of the reflected grid on this surface. And if a loading that is depicted by these red arrows is applied to the reflective surface, it will generate local slopes. And these slopes will make that this will not be point P that is reflected, but now point Q from the grid. And if we have an image without loading, we can get as well an image with loading and as a function of time, since we are using high-speed cameras. And it's quite easy to show that the distance PQ between these 2 points can be related to the phase difference between those two images. So at the end, we can really have simple geometrical relations between slope fields and the spatial phase map that we can calculate between consecutive loaded images or consecutive images with loading and a reference image without loading. And what the only two quantities that we need to know are the spacing between the grid and the reflective surface, so L, and the pitch, the spatial grid period. And if you know P and L, then you can derive the slopes in X and Y directions from spatial phase maps, which is quite direct and so simple to set up. So just for fun, I would say it's not that new, because I found it in a book which is entitled Scientific Experiments of Ontario Science Centre, and they show that using a can, a small mirror, an inflatable balloon, and a flashlight, you can at the end make deflectometry at home. So in this case, when the young lady speaks in front of the can, so there's a partly reflective membrane that is mounting at the other end. In fact, the reflected light beam from the mirror is deflected on the wall following the voice. And if we make a zoom on that part, so there is lighting, there is an excitation that is applied to a vibrating and reflective membrane, and then there's a deflected light beam. And this light beam would be, in our case, recorded by a digital camera. And that's what we do in real life. So this is actually a setup in the hemianechoic room at Sherbrooke. There is the printed grid here, and a reflective panel. So sorry for the tilt from PowerPoint. So there is the printed grid. So this is reflected on this panel that is simply polished using core body polishing techniques, and this is typically the image of the grid that is captured by the high-speed camera So the grid is generated using any vector drawing program. It's printed out on a standard that past the printer, and finally it's glued on a particle board. So this is here a comparison of what we got between on the left a laser vibrometry measurement and on the right a deflectometry measurement. The measurement area for deflectometry is smaller because we did it quite simply and we did not want to move the panel, so the observation area was a little bit smaller for the case of deflectometry, but whatever. So this is the response of a simply supported panel at the sine excitation which is applied with the shaker, and the frequency is 525 Hertz. And the comparison is quite informative. For the laser vibrometry measurement, we got here a mesh of 43 times 37 points, which make a little bit more than 1,500 points. The spatial resolution is 1 centimeter, and the acquisition time is 15 minutes using the fast scan operation. For the deflectometry, in a smaller area, we got 21,000 measurement points that are spaced by 2.1 millimeters, and the acquisition time is smaller than 1 second. So this makes quite interesting ratios or multiplicative constants, because we got 13 more points. The spatial resolution is divided by a factor 5, and the acquisition time divided by a factor nearly reaching 1,000. So I put here some examples of what we can do with this. So we perform some mechanical impact identification using an instrumented impact hammer, and we shown that coupling deflectometry measurement to force identification methods led to really accurate results. So we can recover the magnitude, but we can recover the force as a function of space. So on the left, you got the spatial displacement as a function of time, and on the right, you get the reconstructed force. So you'll see that when the plate is impacted, you see an impact right there from my pointer. I'll replay it. So yeah, that was really quick, but then we got the spatial and time resolved vibration field on the panel, which is fantastic. Then another example is steel marbles. So we dropped steel marbles on the panel. So this is a non-instrumented excitation, and we do not know nothing concerning the excitation. So we were able to reconstruct the load time history at the 3 impact points, and even generated a 4-dimensional graphic that combines the time history. So time is coded here using color. So black is the first, then dark blue is the second, and light blue would be the third impact. And this is depicted as a function of space, x and y coordinates. And on the z-axis, this is the magnitude of the reconstructed force. So that's pretty convenient as a representation. this is really interesting. Definitely, deflectometry is fantastic. Contactless, high density, time resolved vibration measurements. This is limited to plane surface, but that is okay because most of the laboratory applications involve plane structures. But maybe the most limitative aspect is that this is limited to specularly reflective surface. So the the main problem is that this requires mirror-like surfaces. So you can polish the surface, but you can also glue or add a reflective mylar. That is okay. So this was studied at CAV in 2020 by Gary Rhodes. That was the subject of his master's thesis. But the problem is that since you have to add something on the structure, you're like being limited by the fact that you'll never measure the structure only, but the structure with an additional film or damping on it. So this solution is to move to infrared deflectometry. Why? Because Rayleigh's criterion to ensure that specular reflection is dominant is that the ratio of the wavelengths, the optical wavelengths, divided by the surface roughness here, multiplied by cos theta, theta being the angle of incidence, and this ratio should be over 8 to ensure that we are mostly in the presence of specular reflection. And in the visible spectrum, the wavelength is approximately 500 nanometers, so it requires a roughness of 60 nanometers for specular reflection. And if we go to infrared spectrum, then the wavelengths will be approximately 10 micrometers, and then the roughness will be now 1.25 micrometers. So this really relaxes the constraints, and it shows that these are some examples from a paper of Toniuk and Pierron, and you see that plastic like ABS will not show a grid, whereas using infrared we'll see a reflected grid on these structures. So you can find the corresponding paper that was published in Applied Acoustics this year. And so the idea is to make exactly the same things using optical visible deflectometry, but using an infrared high-speed camera. So that's what we did at GOES. And we compared the two techniques on a simple cantilever beam and their impact. So there is one side with a mirror-like finish, and the other side is left unprepared. And we used a miniature impact hammer to test the cantilever beam. And so we used either a visible high-speed camera, a printed grid, and a measurement on the mirror-like side of the beam. And then we flipped the beam, had a look to the unprepared side of the beam, use an infrared high-speed camera, a thermal grid, and make this measurement like this. So the thermal grid is required because we'll use the difference in emissivity between printed plastic and an aluminium to produce a contrasted pattern that will be finally reflected on the beam. So the results are that so on the upper graph you got the results for optical visible deflectometry. So the orange arrows indicate the modes of vibration, flexural vibration of the beam. So you got mode 1, mode 2, mode 3, mode 4, and mode 5. And here you got the first torsion mode. For the infrared deflectometry, the modes are all well identified but the measurement is a little bit noisier. And why? Because there's still a cooling Stirling engine on the camera that generate vibrations and especially contents that are located at multiples of the rotation frequency of the cooling engine. So a possible solution to this is simply to be able to put this engine off during the acquisition time, which is quite reduced because it is of the order of a second. But anyway, the two techniques allows to identify precisely the frequency of the modes, but also allows to have a really clear and neat mapping of the vibration field of the beam. And just to recall, let me recall that these were obtained using less than 1 second measurements, and using this you can really have an impressive precision on the mapping of the vibration modes on the beam. So to conclude, the results that are shown you have a density reaching an impressive value of 200,000 measurement points per square meter for visible deflectometry, and that were obtained at a rate of 30,000 frames per second. But this requires a mirror-like surface. Concerning infrared deflectometry, the results reported have a density of 25,000 measurement points per square meter and at a rate of 3,000 frames per second. But the main asset is that these kind of measurements can be performed on common material with common surface condition, but a thermal grid is needed. But this is not that difficult to set up because an heated grid with materials that have contrasted emissivity values will be okay. So the last point is that, yeah, the cameras that are used for visible and infrared deflectometries have different technical features. So since they have different sensor dimensions, this directly influence reachable time and space scales. But high-speed infrared imaging is still an emerging technology, and we expect that it will be developing quickly, as it was the case for visible high-speed imaging. The key advantage is that all the established methods and algorithms for image processing are just identical. So if you got a toolbox for post-processing the images, then it can be directly applied to visible or infrared deflectometry. So at the end, you get a broader range of materials and surfaces that can be tested using the deflectometry technique. And the next steps are to develop backlit grids using a TV screen, which would be more flexible than printing the grid on particle board and so on. And we are currently digging into a new post-processing approach, especially approaches that are inspired from a particle image vesselimetry. So thank you for listening, and I'll be happy to take your questions.
Okay, thanks, Olivier. I don't know if you could hear the applause, but we gave you a hand. Is your microphone working? Okay, so for some reason, Olivier, I think you're in a system that you have to type answers in. Any questions from the audience? Once again, wait for Melissa or Kelly to pass you on a microphone. Okay, so Olivier, I have one. I'm always interested in the force inference. I know you didn't present the theory for that, but in general, how many random forces, I'm thinking of the marble problem, do you think the methodology can handle? Is it in the order of just a few, or can you go up to hundreds of individual random events? It's probably going to take him a while to type an answer. I should probably limit questions to yes or no or numbers, but. Hold on. A microphone is coming towards you.
Yeah. Could he address the difficulty moving to apply this method to curved surfaces? Because that's
Okay.
usually what one thinks about in practice.
Oh, have we lost Olivier? I'm still looking at his. So I don't know if he can answer or not. I'll put Dr. Shepard in the spot. Do you recall what Olivier was pursuing for curved surfaces? Here comes the microphone.
I don't know specifically what he is looking at, but the theory does need to be reworked. There's a special relationship that he had between the angle, the rotation at a point, and the length between the grid and the structure and the pitch. You have to rework that theory, and I think you could do that fairly easily for a small curvature. Larger curvature, I think would be probably require multiple cameras, but probably could be worked out as well.
Okay, so I think we'll forego further questions that Olivier can't answer. But if you do have anything for him, please go ahead and reach out to him. I think his contact info is on there. If it isn't, reach out to me. I'll get you in touch with him. You can probably certainly find him on the Sherbrooke website as well. Okay, so that's it for our short introductory session.